Today's flip lesson is over probability, and more specifically, the probability of an event happening. And to find the probability of a certain event happening, we have a formula. The probability of an event is equal to the number of ways that that event can occur over the number in the sample space. So if you'd like to write that down, there are the words. And let's get that in the screen. There we go. You can pause that and write that down if you'd like. The way I like to look at it is that the number on the top is what we want to happen. The number of the bottom are all the things that could happen. So we're going to go straight to an example. Some of you have said, oh, Ms. Overby, can't you do examples in your flip lesson? Well, today's lesson is a perfect time to go straight to examples. And so here we go. Example 1. 2 quarters are tossed. What is the probability that both land heads up? Now, I could spend my time and flip the quarters and watch them land, and that could be fun, but we'd of course be wasting our time. So I'm going to remember that eventually I'm going to have to use this formula. And so first of all, I want to know in how many ways can the event happen? Well, there's only one way you can get 2 heads, and that's if both coins land heads up. So there's only one way to have this event happen. But in our sample space, this is our sample space here, that means how many different ways could throwing 2 coins end up? We could get the 2 heads, or we could throw our coins up and one of them could be heads, the other tails. Another option would be the first one's tail, the second one's head, and the fourth option is 2 tails. So if you're doubting this, go grab 2 quarters and start throwing them. Well, maybe not throwing them, but you know what I mean. And see if you can come up with any more than 4 different ways that it can occur when you throw 2 coins. But that's it. That's all we have. And so to find the probability, let's speed everything up. To find the probability of throwing or getting 2 heads after throwing 2 coins is going to be 1/4, because once again the 1 stands for how many ways could the event occur. Just one way, getting heads and heads. And on the bottom is how many different ways are in your sample space. How many different ways could it actually occur? So there's only one way to get what we want and 4 ways that it could actually work out. So that was example 1. Example 2, we've got 2 6-sided die that are being tossed, and we want to know the probability that a total of 7 is rolled. And so once again, we're going to use our probability formula that says find the number of ways that our event could occur over the number that are in our sample space. So let's see. What we want is the number that goes on top. We want a total of 7 that's rolled. So let's see. We could do it where we rolled a 1 first, then a 6. Or let's just get that over with, a 6 and a 1. How about a 2 and a 5? 5 and a 2. How about a 3 and a 4? And a 4 and a 3. And are we leaving any way out? I don't think so. So we're going to have 1, 2, 3, 4, 5, 6 ways that our event can occur. But obviously, we're going to have a lot more in our sample space, because when we start rolling, we can have a 1 and a 1 and a 1 and a 2 and a 1 and a 3. And I could keep going, but gosh, I remember a shortcut for doing this type of problem, and that's to draw 2 lines and use the fundamental counting principle. When I am throwing the first dice, then I have an option of 6 choices that could come up, either 1, 2, 3, 4, 5, or 6. Same thing when I'm throwing that second dice, 6. So I know that I have 36 6 options in the sample space. And so the probability, and now this time I'm going to actually write, this is the fun part of the probability problems. You can actually write after the P what you were taking the probability of. So the probability of taking or getting a sum of 7, let's see, on the top we have 6 ways that can give us a sum of 7, and on the bottom we have 36 possibilities in the sample space. So we can reduce that to be 1 over 6, and that's our probability. Okay, not bad. So let's go ahead, since this is our example lesson, let's look at example 3. Example 3 says, one card is selected from a standard deck of 52 playing cards. What is the probability that the card is either a heart or a face card? And the first question I always get is, what is a face card? And simply, a face card is something, a card with a face on it. So, let's see, we've got the jack has a face, the queen has a face, the king has a face. Ace does not have a face, so ace is not a face card. So it's just a little reminder. So what we're going to look at is we're going to look at what's the probability that we have a heart. So let's see, we've got 4 different types of suits, and we have 52 playing cards. So we're going to divide 4 into 52, and we get what, 14? So we have 14 hearts, so that's the probability of hearts. And then we've got the probability of face cards. So let's see, how many different ways, oops, I'm sorry, I skipped a step. We have the number of hearts that we have would be 14, but the probability of getting a heart would be 14 over 52. What we want would be a heart, so there's 14 hearts, but the total sample space is 52, that goes in the bottom. And same thing with the face card. We've got, let's see, let's go back to the face cards. We've got 3 different faces, and each there's 4 jacks, 4 queens, 4 kings, so altogether there are 12 face cards. So the number of face cards is 12 out of a total of 52 cards. And so we see the word or. If we go back up to the word problem itself, and it says, what is the probability that the card is either a heart or a face card? So what we've done so far is we found out the probability of a card being a heart is 14 out of 52. And the probability of being a face card is 12 out of 52. But this is saying, what's the probability that the card is either a heart or a face card? And so you can hopefully see this on the very bottom. We see the word or, which actually means union. Now, not sure if you remember union and intersection from when you did Venn diagrams. Hopefully that's going to come back to you. But a union, we're going to kind of scoot everything up. A union, which is with the U, looks like this. Probability of a card being a heart or a face card is actually the 14 over 52 plus the 12 over 52, which would give us what? The 26 over 52. You think that's our answer? Oh, let's get the paper that says, is that the right answer? Okay, it's not the right answer, and I want you to think about that. Something's wrong with stopping here. I agree, union, which means the word is the word or, and it actually means add. I don't know if any of you noticed that, but when we're saying a heart or a face card, it's saying both are options, both are possibilities, so we're going to include both. But if we stop here, we're going to get it wrong. And if you haven't figured it out by now, I'll give you a little hint. How many times do we count the Queen of Hearts? So let's think about this. We counted her as one of the, let me scoot this down. We counted her as one of the 14 hearts. We also counted her as one of the 12 faces. So we've counted her twice. Have we counted anybody else twice? So, to correct our mistake, we need to find the probability of a card being both a heart and a face card. Or in other words, we need to find this. Okay, so let me start getting some other things away. All right, so let's look at what we're talking about. We had, let's get this up here. Okay, so this was our answer on the top, but we realized, wait a minute, we're counting some cards twice. That's the Queen of Hearts is counted as a heart card and as a face card, and so we know we need to adjust for that. So we need to find the probability of being both a heart and a face card. So notice here the U is an or, so it's a union and it's an or. And the upside down U means and it's an intersection. Now I know if you forgot your set theory and your Venn diagrams, we're piling on another concept on top of probability, and so you're just going to have to kind of double up on your studying. The way I remember it is this upside down U reminds me of an N, and the N is in the word and. I think about when things intersect, they have to be in one group and in the other group to intersect. So it makes sense if you really think about it. So we need to find out, hey, what's the probability, first of all, of having a card that's both a heart and a face card. And so remember what probability is. The number of ways that our event can happen. So let's see, how many cards that are hearts are also face cards? Well, let's bring back our face cards. And we're going to have what? Jack of Hearts, Queen of Hearts, King of Hearts. That's it. They're going to be 3 cards out of 52 cards altogether. Alright, so we're taking the long way to get to this problem, but I didn't want to jump straight to the formula. But this is what this requires. Anytime we see a problem like this, it's going to require us to do the following. We're going to take the probability of something or something happening, like the probability of it being a heart or a face card. Then we do find the probability of each individually and we add them together. But if certain events are not mutually exclusive, we have to subtract the probability of the intersection of A and B. So when it comes down to this, let's see, we got to finish this problem, don't we? I'll flip over this one. So here we go. To find the probability of a heart or a face card, we already said that the heart was probability of a heart. Let's see, let's write it this way and then we'll come back in and fill the numbers. Plus the probability of a face card. Alright. Minus the probability of a heart and a face card. So when we fill in the numbers, we're going to say, okay, probability of being both a heart, probability of drawing a heart or a face card is equal to the probability of a heart, which we already figured out was 14 over 52, plus probability of face card is 12 over 52. And then it's minus the probability of being both a heart and a face card, which we had just said was 3 over 52. So that gives us what? 26 minus 3 is 23 over 52. Alright, so sometimes we're going to see problems like this. And these type of problems are called taking the probability of the union of two events happening at the same time, picking a face card or a hearts. And if it's like the problem we just did, I know it was in the formula. If it's like the problem we just did, we have to take into account that after we're done adding the two probabilities together, we've counted some things more than others. We've counted some things twice, and we have to subtract. We have to make up for that and subtract the intersection of the two. If you have two events that are mutually exclusive, for instance, if this was the probability of picking a heart or a club, then all we would have to do is find the probability of picking a heart plus the probability of picking a club, and we've done. Because you can't be both a heart and a club, like you could be a heart and a face card. Okay, a lot of words, I realize that. Hopefully you're able to pause and write down notes, and if this example is still confusing you when you get into class, ask away. We're going to see problems like that in the homework, and I can help you in class. All right, another concept we're going to be looking at is called independent events. We just talked about, real quickly, mutually exclusive events, like picking a heart and picking a club. But now we're going to talk about independent events, and they sound similar, but let me give you some examples of independent events. Flipping a coin and tossing a dice, right? If you flip a coin and you get heads, then that's not going to influence your result when you toss a dice, right? If you toss a dice, it didn't say, oh man, you know, I got a tail on that flipping of a coin, I'm feeling bad, I'm going to go for that lucky 6, I'm going to get a 6, right? No, I mean, it would be freaky if coins and dice thought that way. So they're two independent events. Or even flipping a coin and then flipping it again. That coin's not going to say, you know what, it's time for, you know, tails now. And so they're two independent events. Or choosing a marble out of a bag with replacement. So imagine a bag with marbles in it, maybe, you know, 3 red and 5 blue. If you pick out a red the first time, certainly if you don't replace it, then your next pick is not going to be independent of your first pick. But if you replace it and start all over again, then the next pick is independent of the first. So another concept that we can talk more about in class, you're going to see probability problems with independent events, and I want you to know what to do when you see those. When we do see them, we can find the probability that both of them will occur by doing this. The probability of A and B, and we've talked about this a little bit, that how the word and in counting principle problems and in probability now is going to mean multiply. So the probability of two independent events, A and B happening, is just equal to the probability of A happening times the probability of B happening. And so it's going to lead us to our fourth example. And our fourth example is this. When tossing a quarter, what is the probability that tails will occur on the first 5 throws? First of all, you ask yourself, okay, we have 5 different events. Each toss, each throw is a separate event. Are they independent events? Yes, quarters do not remember what their result was from the event before and try to make up for it. Each throw is independent of the result of the previous throw. And so to find the probability, you know, you can get creative. You can write probability of T and T and T and T and T to represent your 5 tails, or you can just write probability of 5 tails in 5 throws. But what it comes down to is saying, okay, the probability of getting tails from the first throw is 1 over 2, right? There's only one way to get tails, and there are 2 in the sample set, either tails, heads, or tails. And so each throw is just going to be, the probability is going to be 1/2. So we have 1/2 times 1/2 times 1/2 times 1/2 times 1/2, which is 1 over 32, which sometimes I like to change fractions. This is the only time I prefer decimals than fractions, or one of the only times, because when I look at the 0.03%, it's like, whoa, The probability is not very high that you're going to get 5 tails in 5 throws of a quarter. So we only have one more thing left. Yay! And our last thing is finding the complement of an event. And it's not saying, oh, that event was well done, it was so enjoyable, that was the best event ever. Not that kind of compliment. The complement of an event A is denoted by A prime, and I hope you can see that little prime right up there. And so what does that mean, the complement of an event? Well, basically it means this. There are two things that can happen. Either the event happens or it doesn't happen, and the sum of those two things has to equal 1. Kind of like this. What if we think about the probability of it raining or the probability of it not raining? So the probability of rain plus the probability of no rain is going to add up to 1. The probability of winning a lottery plus the probability of not winning a lottery is going to add up to 1. And so what we're going to use the complement of an event for is when we see problems that maybe say, find the probability of something happening, at least 99 times. We don't want to do the probability of 1 and the probability of 2 and the probability of 3. We're going to use this complement of an event to find that type of probability. So now you have everything you need at your disposal. I will tell you, however, that when we do the problems, and boy, let's just put a whole bunch of stuff down here while I'm talking so you don't have to stare at my wood floor. When we do the probability problems in class, I will tell you that we are going to be using NCR and NPR. Did we today? We used the counting principle to find a sample space of the dice problem, but you'll find that in our homework problems in class, we will be using NCR and NPR, and that will be a lot of fun. As always, the most fun we're going to have is going to be tackling those problems in class, and I really look forward to tomorrow helping you with the fun of doing probability problems. And I'll see you in class. Thanks.